Hi, so I'm Gary White. I'm a senior data scientist at Huawei, and I'm going to introduce you to SLMAD, which is our statistical learning-based metric anomaly detection framework that we have submitted to AIOPS at ICSOC. So in this presentation, we're going to go through the background of the problem, going to give you some additional information on the context of the problem, and then we'll go through in detail the actual SLMAD algorithm design. Then I'll show you some of the experimental setup that we use to evaluate this algorithm and see how it performs on a number of different datasets and against a benchmark algorithm. And then I'll show you the results of those experiments, some of the conclusions that we've learned, and the future work that we're hoping to do in the coming few years on this topic. So some of the background to this problem is that in cloud applications, we can have a huge range of metrics that we want to track and make sure that our customers are having a quality experience. This is especially the case in Huawei, where we have a huge number of different services that can have their own metrics, and we want to be able to make sure that across our range of products that our users are having this good experience. So we want to track a number of different metrics from CPU usage, response time, jitter, and metrics such as this. So with a large range and quantity of different metrics, it is difficult for a human operator to follow, and therefore an automated approach is needed to detect anomalies and to alert potential incidents in real time. So once we have these huge global scale cloud networks, it can be very difficult for a human operator to look at all these different metrics and to make a decision across all of them. So the operator needs some help from an algorithm, in this case an anomaly detection algorithm, to help point out when services aren't performing well. And finally, one of the additional contexts we have for this problem is that in production nodes, there's a limit in the amount of resources available for monitoring and maintenance, so the solution must be as lightweight as possible. So it's obviously no good having a monitoring and prediction approach that uses too much of the resources, even if it is incredibly accurate, because you're taking away from the actual user who you want to be making the most of this production node. So some additional context that we have in this problem. So there are a number of particular challenges that are posed in the construction of a desired industry-grade time series anomaly detection framework. And so the first most obvious challenge that we had was the lack of labels. So in production level business scenarios, the system often produces millions of different metrics, and there is no easy way to automate label data on this scale manually. Moreover, if the time series is in a dynamic environment where the data distribution is constantly changing, then the model will need to be retrained frequently on new data. So labeling this data can introduce a significant delay in cost and need to be continuously updated with the models. So this makes supervised models insufficient for the industrial scenario because you can't keep labeling this data because due to the frequency and the amount it would cost. So we really felt that we needed to add an unsupervised approach for this particular use case. The second context to this problem is generalization. So there are a huge number of different metrics and scenarios that time series anomaly detection can be applied to. So time series data is almost everywhere in cloud systems, and in a production environment, the time series data can exhibit a range of different patterns and variability. So industrial anomaly detection must work well on all kinds of time series patterns. However, some existing approaches assume the shape of the data, and they are not designed to adopt to different patterns. So our time series or anomaly detection algorithm really must be able to be applied to a range of different data sets. The third point in the context of this problem is efficiency and accuracy. So in production scenarios, a monitoring system must process millions of time series in near real time. So this is especially important for sub-minute level time series. The anomaly detection procedure needs to be finished within a limited time, so i.e. before the next data point. Furthermore, if the monitoring and anomaly detection system is running on a production node, then it must not use a lot of the computing resources to respect the quota assigned for customers. Therefore, even though the models are large time complexity, even though if a model has large time complexity and may achieve good accuracy, they are of little use in a production scenario because they're taking away too much resources from the actual user. Some other challenges that we had in the construction of this framework was for online training and updating. So once trained, the model should be able to update online as new data is collected. So many of the existing algorithms that we looked at are designed for settings that send data in batches rather than runtime streams. So this can lead to an old model being used until the new data has been updated. So in a dynamic environment where the data can change suddenly, using an old method can lead to a decrease in anomaly detection algorithm accuracy. So we wanted our models to be able to update online. The final context that we had for this problem was parameter tuning. So the existing anomaly detection algorithms that we had looked at, they require a lot of parameter tuning to generate meaningful results. So for example, a neural network or deep learning based method requires tuning of optimal hyperparameters and window size for each metric. This can become complex and time consuming in production environments with a large number of metrics. An approach that can automatically set these parameters or requires little parameter tuning can be more easily deployed in a production environment. So this is the overview of our SLMAD algorithm design. So you can see that there's 3 quite distinct stages. So in the first stage, we do some analysis on the time series. Then in stage 2, we have this dynamic grouping stage. And finally, in stage 3, we do the model training and evaluation. So we'll go into more detail in these in the next few slides, but so the main context for the analyzing the time series is that in this stage we're performing statistical tests which are used to determine the characteristics of a subset of the data. So we evaluate the data set to see if it's stationary, discrete or continuous, and whether there's any seasonality. So this goes into automating some of the decisions about which algorithm that we should use in stage 2. So in stage 2, we do dynamic grouping and use the output of the analysis stage to determine which algorithm to use. So if the time series is stationary, continuous and seasonal, we use dynamic grouping approach to build multiple box plots. If the time series is not stationary, continuous and seasonal, then we use a matrix profile based algorithm. So finally, in stage 3, we train the model and evaluate them with new data. So the results can be saved to a file, we can visualize them or use them as the start of an automated remediation process. So this overall framework has a number of different advantages. So one of the main ones that we tried to focus on was the lack of labels. So in production level business scenarios, the system produces a large number of metrics, and this approach has been designed basically from the ground up to be unsupervised, so it doesn't require any labeled data. The second advantage it has is that it's very generalizable. So thanks to the stage 1, where we analyze the time series, we're able to set a number of the parameters that we use for our algorithms automatically, so it doesn't require any human input. The third advantage we have then is that the framework is very efficient, so it has been designed to consume few resources, and due to the large amount of metrics that are needed, this can increase the amount that we can process. And finally, our time series is able to update online. So the time series metrics can change characteristics over time, and our models are able to update it as new data is collected. So in this slide, we go into a bit more detail on each of the individual stages. So in stage 1, where we're analyzing the time series, we first used statistical methods to evaluate a small subset of the time series in terms of its characteristics. So we check whether the time series is stationary using the augmented Dickey-Fuller test and the KPSS tests. So if both tests conclude that the time series is stationary, it is labeled as stationary. If only the ADF test confirms that the series is stationary, then it is labeled as different stationary. And if only the KPSS test confirms that the dataset is stationary, we label it as trend stationary. We then check the time series to see if it is discrete or continuous. If there are more than 20 distinct points in the dataset, then we label it as continuous, otherwise it is discrete. Finally, we check whether the time series is seasonal by using autocorrelation. So if seasonality is detected, we find the best period. The seasonality analysis and period determination methodology are given in figure 3, which you can see on the left. And if the autocorrelation is over 0.9, we label the data as seasonal. So we then determine the best period using the peaks in the time series and calculate the number of points between the peaks as the period. So this analysis is very useful in stage 2, where we do the dynamic grouping. So based on the output of the analysis stage, we build the following 2 cases. So case 1 and case 2. So in case 1, we provided that the time series is stationary, continuous, and seasonal. We use a subset of the data as a training set and group them based on the best period using a dynamic grouping approach. So since at least 5 points are needed to build a box plot, we use equal to 5 or more periods and then group them based on that. And then we create a box plot for each of the individual periods and we update them as new data is added. So if the time series does not possess all the aforementioned characteristics, such as being stationary, continuous, and seasonal, we use a matrix profile for streaming data to determine the discords in the time series. So the top discords are the anomalies, and we label those as anomalies. And we select the matrix profile as it can work without the need for parameter tuning, and it does not assume the shape of the time series. So finally, in stage 3, which is model training and evaluation, we train the models and evaluate them on new data. So we build models for case 1 and case 2 in the dynamic grouping stage separately, as explained below. So in case 1, for each group, we build at least one box plot. So for example, if the best period is 10, we use at least 50 points to build the models in the training set. In other words, 10 box plot thresholds are constructed. So in case 2, for the matrix profile, we capture the latent features in the time series data, and then this is used to identify the discords, which are the sudden changes in the time series that identify the anomalies. The models are updated at runtime, and so for case 1, we update the models, we update the box plot threshold for each group as soon as we collect data equal to 1 period. And for case 2, we update the matrix profile for each streaming data point. So the results can then be saved to a file, visualized, or used as the start of an automated remediation process. So this is the experimental setup that we had to evaluate our approach. So we used multiple different data sets, including an open source anomaly detection benchmark and some in-house Huawei network production data to evaluate our approach. So the open source benchmarks that we used were the new Menta benchmarking suite. We also used some data from Yahoo. So Lab 7 had released an open source anomaly detection dataset. And finally, we had our in-house Huawei production data. The evaluation metrics that we used to evaluate this algorithm was a mixture of standard accuracy metrics such as precision, recall, and F1 score. We also evaluated the efficiency and resource course of our approach using an implementation in Go and Python to evaluate the impact on packet size, CPU utilization, memory utilization, training time, and testing time. And this was important because being able to be resource efficient was one of the requirements of this algorithm. So these are the results that we got for our algorithm. So looking first at table 2, which was evaluated on the Menta dataset, we can see that our approach achieves very good precision and recall as well. And so the F1 score for our approach was consistently better than the approach that we compared it against. So we compared it against a persistence anomaly detection algorithm. And you can see that for each of the data sets, our SLMAD approach has achieved a higher F1 score. For the Yahoo metrics, we can see that we achieve really impressive precision and recall, and that our F1 score is greater than 90%, and our precision score was greater than 96%. So we were achieving very good results for this particular data set, And I think that can be due to the limited number of anomalies that's included in this benchmark compared to the Numenta metrics dataset. So in table 4, we can see that our approach has again showed better results on all the different datasets compared to the persistence algorithm, which we were very pleased with, as this was our target dataset. So finally, we can look at the resource and efficiency costs for the SLMAD approach. And so we can see that there's a very large differentiation when you're comparing the Golang implementation and the Python implementation. So you can see that there's a huge reduction in the package size, as well as the CPU utilization when the algorithm is used, and as well on the memory utilization. So we can also see how there's a massive reduction in the training time and testing time by using the Go implementation as well, compared to the Python implementation. So the conclusions that we've had from this paper and this work is that our algorithm has been able to achieve a high F1 score with low resource consumption on a large range of datasets. So implementing our algorithm in Golang has helped to dramatically reduce the resource consumption. So we've been able to achieve an average precision of greater than 96% and an F1 score of greater than 90% on the Yahoo dataset, and an F1 score of greater than 70% on the Huawei metric data. So we compare our evaluation against our persistence anomaly detection approach, and our approach shows improved F1 score for all the datasets we tested on when compared with this algorithm. So we have a number of different projects lined up as future work. So detecting that there is anomaly is only the first step in dealing with changes and unexpected behavior in an automated way. So we plan to evaluate our framework against a number of other state-of-the-art algorithms on anomaly detection data that we've collected. And then we plan to use this anomaly detection system to trigger root cause analysis to provide further context on why the anomaly happened, and also to feed these anomalies into an automated remediation system to automatically recover from application faults and anomalies. So that's my presentation on our SLMAD framework, and I'll take any questions that you have.